Hello, everyone. I'm Anton. I'm a PhD student at the University of Groningen, and I work with Helle and with Clemens. And I'm going to present you something that we did together, which is this dual adjunction between Ω-automata and Wilke algebras. And I'm going to spend quite some time actually explaining what these are. So don't worry if you hear them for the first time. So in general, we're going to talk a lot about automata, and well, what do we normally mean by automata is just some abstract model of computation. And it turns out that very often these models of computation are very nicely related to formal languages. And by formal language, we'll just understand some sets of words over some alphabet. And we have some examples, of course, non-exhaustive, of some types of automata and classes of formal languages. And I guess one of the main ones is between finite state automata and regular languages. But there are many more, of course. And the question that arose at some point was, can we also characterize languages of infinite words with automata? So because normally when we say formal languages consisting of words, we mean finite words, so finite sequences of symbols from the alphabet. But then one could just as well define sets of infinite words. So infinite, let's say as in sequences over the natural numbers, not too infinite. And so for characterizing some nice classes of languages of infinite words, Büchi came up with this notion of Büchi automaton. And we can see that it's actually its definition is, at first it looks the same as just a standard finite state automaton. So it has some states here in this picture, Q1, Q2. It has some transition relation labeled with symbols from sigma. It has some initial states, in this case only Q1, and some final states, in this case only Q2. What actually differs from DFAs or NFAs is how we actually determine whether some word is accepted. And so this infinite word alpha is accepted if there exists some run in this automaton that starts with some initial state and it visits some final state infinitely often. So it doesn't really ever terminate somewhere, but it keeps going on, and it needs to visit infinitely many times a final state. And here we can see a word has to start here in Q1 and it has to go infinitely many times through Q2. And well, this is actually just a language that has infinitely many B's in it, because we can get into Q2 only with reading a B. So this automaton accepts the language of all words that have infinitely many B's. And so now we get this notion of an omega regular language, which is just a language recognized by a Büchi automaton. And well, first we see that they're called omega regular. Well, it's not no coincidence. They actually share many of the nice properties of regular languages. So we have closure under Boolean operations. We have this sort of description with omega regular expressions. But we're going to focus on some other property here, which is this property related to the notion of an ultimately periodic word. And well, I'm going to say that for some omega regular L, we have this ultimately periodic fragment of L, which is just all the ultimately periodic words that are in L. And by ultimately periodic, this means a word of the form u v to the omega, which is just a notation for u, v, 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 and so on, repeating v infinitely. And there is this very nice property that if two omega regular languages have the same ultimately periodic words, then they are the same as, like, all of them are the same. So in fact, this means that if we just want to characterize some omega regular language, it suffices to characterize its ultimately periodic words. And there are, I claim, yes, Ezra?
Sorry, just a quick question. So is it actually the case that the ultimately periodic words are dense in an omega regular language?
Under what topology?
Like the counterspace topology. Or just the topology generated by the cylinder size.
I haven't thought about this.
Okay, then we'll talk about it after.
Okay, but thanks. So, I was saying that we actually, what was the benefit of working with ultimately periodic words is that they are a lot more binary. And what I mean is, now I'm going to explain with this notion of a lasso. Well, I'm going to represent ultimately periodic words as lassos, and a lasso is just such a pair u comma v, where v is non-empty. Well, because the repeating part of the word has to be non-empty, and then this u comma v here, it just represents the ultimately periodic word u v to the omega. So it's just a, let's say, a nice way to represent an ultimately periodic word without referring to the infinite sequence, but just a pair of two finite words. And now we can speak of lasso languages, which are just sets of lassos. And in particular, for an omega regular L, we can speak of its lasso language, which is all the lassos that represent an ultimately periodic word inside of L. And then by the statement from the last slide, it actually means that if we're able to characterize this set lasso of L, we immediately know what L is. I mean, we have determined it uniquely. Maybe we don't know exactly what it looks like, but it's at least determined. And so there is this idea that at some point came up, which is to build on. So instead of working with some Büchi automaton, maybe try to come up with an automaton that accepts lasso of L instead of L. So it accepts this lasso language. And so now we're going to talk about this notion of an automaton, which was introduced by Chancha and Feynman. And so it's called a lasso automaton. And this admittedly is slightly more different from DFAs, but not too much, actually, we'll see. So it has two sets of states, these x states and these y states. And it has three types of transitions. So this red transition, red type of transitions is between x states. We have this green type of transitions between x states and y states. So starting from x state and going to y states. And then the blue transitions, which go between y states. And then we have an initial state. So let me just point out, these are deterministic transitions here. We have an initial state, which is always an x state. And we have some final states, which are always y states. And now how to make sense of this in the sense of accepting lassos? Well, we say that the lasso language of L is, it consists of all these lassos, u comma v, such that we have the following. We have a run starting at the initial state. We read the first component along red states, and then we read the first letter of the second component along a green state, green transition, and then the rest is read in the blue transitions. So in fact, these green transitions will read only a single letter every time. And then we want to end up in final state. in order to accept the lasso. So it's I would say it's very similar to DFAs, really. It's just that we have two sorts of words that we want to read with with separate transitions and separate states. Okay. And now something that I want to mention, which is neat, is that something that's not so easy to do for Büchi automata is to make algebraic or co-algebraic sense of these Büchi automata. But for lasso automata, we have it. We have this being the case that well, if I take a lasso automaton but remove its final states, it is an algebra of this type over set times set. So if we see this functor, well, this arrow is actually two arrows from this set to x and from this state to y. And these arrows are actually the, well, I'm abusing notation a bit, but I imagine now S is an arrow from 1 to the initial state. And then I have the first transition type, and then the rest of the transition types. And similarly, if we remove the initial state of a lasso automaton, we get a coalgebra with the first two transition types, and then the last transition type and the final states seen as a function from the states to 0, 1.
And somehow you change of sides with tau. I think the tau is used on the earlier slide with the psi and the tau are basically the same.
Let's see, was there a tau in the previous slide?
It's not also side.
Yeah, it's tau.
Oh,
the signature
okay,
side.
here there's a tau.
Ah, okay, right.
Oh, my bad. But it has to be xi. Yes.
Okay, so tau should be psi.
Yes, it will be xi. Yeah, to be honest, I struggle also to keep track of what the letters are, but they apparently always are the same. Now let's actually, yes.
Why did you remove the initial and final states for those two things on the previous slide?
Yeah, well, can you repeat the question?
So what's the reason why the first one doesn't have a final states and the second one doesn't have initial states?
So as far as I know, for example, from the world of DFAs, this notion of final states is not really an algebraic notion, or so the initial state and the transitions have a neat algebraic representation, but the final states, they are really like an arrow going out in a sense, which is much nicer to view as a coalgebra. Well, I don't even know how to view it as a coalgebra, really the final states map. So then we just have to get rid of it in order to model algebraically the rest of the information we have.
Couldn't you add another constant and then include that for the final states? So
to add constants for
the same way the initial state is defined, you could define a final state.
yes. So thing is that
There's not always one.
yeah, okay, but I don't really have access to the whiteboard.
Okay.
So it's okay. Maybe I can show here the final states. They can be seen as an arrow from Y to the two element set. But then I'm not sure how would you see it as an arrow from something to Y. It's
You need to choose you need to know how many final states there are and put a constant there.
right, but I don't want to know how many there are because I want to allow any number.
Right.
And maybe also if we see our arrows in our category as going forward in time, then you want to start with your initial state and you want to end with your final state.
Okay. Fair enough.
Yeah, well, it's just much neater to think of it algebraically than algebraically, right? And now, but maybe we got a bit distracted because what we actually wanted to do is to build an automaton that recognizes the lasso language of L for some omega regular L. But is it really the case that lasso automata always recognize the lasso language of omega regular language? Well, actually, no. And how we can see it is that if L is omega regular, then lasso of L is saturated, which means that if there are two ultimately periodic words represented in two ways as lassos, so as the way U1 V1 and as U2 V2, you see these lassos represent the same ultimately periodic word. Well, then they both have to be accepted or both have to be rejected by the lasso automaton. Otherwise, this makes no sense to speak of to see it as a lasso language of an omega regular language. And well, one can easily construct a lasso automaton for which this is not the case, because we only gave some restrictions on what the structure of a lasso automaton is, but you see, just the same way how we can build like many different things with GFAs, with lasso automata, it's also difficult to violate this condition as well. So what do we do? Well, actually, it turns out that as long as this saturation property is satisfied by the language of our automaton, then this lasso language immediately is guaranteed to correspond to the lasso language of an omega regular language. So what do I mean? If we define this omega automaton to be just a lasso automaton with a saturated language, then we have that our language L is omega regular precisely when its lasso language is accepted by some omega automaton, which means both that every omega automaton accepts lasso language corresponding to an omega regular language, and also vice versa, that every omega regular language has a lasso language which can be recognized by an omega automaton. So this is actually what we wanted, the notion that we really wanted. Okay, and now something a bit different. Now I was talking about the automata way to recognize omega regular languages, but there's also an algebraic way. And so if you are familiar with the way that semigroups can be used to recognize regular languages, well, we have similar structures for recognizing omega regular languages. And actually there are a couple, but I'm going to talk about one of them, which is the notion of a Wilke algebra. So a Wilke algebra is an algebra of this type. So it has two sorts and three operations. And this sort, intuitively think of it as the sort of finite word. And this sort, think of it as a sort of infinite words. Or at least all these words are infinite, these words are finite. And then we have these three operations, and then this dot composition intuitively is the composition of two finite words, or concatenation of two finite words. The second operation, this times concatenation, is the concatenation of a finite word and an infinite word. And this omega power is just taking a finite word and taking the omega power of it. And we have some axioms that need to be satisfied, but these are just, let's say, reasonable axioms that we would expect. I'm not going to go over them here. So how does the structure actually recognize omega regular languages? I need some more machinery, which hopefully should be intuitive. So I call Wilke algebra homomorphism a structure preserving map. So just what I would expect by homomorphism. So I have two Wilke algebras. I have a map that maps the finite sort to the finite sort, the infinite sort to the infinite sort, and I want these to preserve my structure. So these operations that I have. And then I noticed that this algebra here, sigma plus, sigma ultimately periodic. So these are the finite words or non-empty finite words and the ultimately periodic words over sigma. This is actually the freely generated Wilke algebra from the alphabet sigma. And now I work with this notion of a quotient Wilke algebra, which essentially is a quotient of the free Wilke algebra. So it consists of some Wilke algebra and this quotient map, and it's essentially well, yes, we see this is this quotient map from the free algebra to our given algebra, and the fact that it's a surjective homomorphism is exactly this idea that it's a quotient. And now we say that a quotient Wilke algebra recognizes a language L if L is the pre-image of some subset of the infinite sort. So in another way, we could say that L is recognized by this quotient Wilke algebra if the quotient seen as an equivalence relation or as a congruence, this congruence saturates well, it saturates the congruence saturates the language, the sets that is the language inside of here. Okay.
Does U more you represent the final state?
This which U? Sorry.
The U that you use,
Yeah.
you take the pre-image of.
What about the U?
So you're saying that L is recognized if it is exactly the pre-image of U by the quotients?
Yes.
So does that mean that U is more the equivalent to like the final state we were talking about when you're looking at the
I would say yes. I think this is a good intuition, but it's a bit dangerous to map one-to-one automatic notions and algebraic notions because they look very similar, but not quite the same. At least in my experience. And now we have this, well, the point of all of this is this theorem by Wilke, which is that if we're given some language L, we have that L is the ultimately periodic fragment of some ultimately periodic language, precisely when L is recognized by a finite quotient Wilke algebra. Which is very similar to like a similar statement we have for semigroups in regular languages. Just we have this slightly annoying ultimately periodic, but apart from that. So now we have two ways to recognize omega regular languages. I mean, we have more ways, but I focus on two ways, omega automata and Wilke algebras. And the thing that we wanted to do is to understand them a bit better, the relationship between the two. And so the result that came out of it is this chain of adjunctions. And there's some notation that I'll explain in a moment. So first of all, this C omega A is the category of co-algebraic omega automata. And co-algebraic, remember, this was no initial state. And this category, I call it the category of algebraic reverse omega automata, op. And I'm going to explain what a reverse omega automaton is in a moment. But first, I need to explain what this adjunction actually is. Well, this adjunction is basically just performing a generalized version of the reverse determinize algorithm. So reverse the states and then determinize using the power set construction. And it actually works pretty much the same way as for DFAs. That's the beauty of lasso automata, that things actually work just the same. I mean, to an extent. So what I mean actually is that actually in the master thesis of Mike Krupman in 2022, he showed that there is an adjunction between the category of co-algebraic lasso automata and algebraic lasso automata up. So that this reverse so if here we have yeah, now it would have been nice to be able to draw somewhere, but I guess it's fine. So the thing that Mike obtains is here co-algebraic lasso automata, here algebraic lasso automata up, and we have the same reverse determinized adjunction. And what we did is we wanted to see here not lasso automata but omega automata, because omega automata for them is a bit trickier because they're lasso automata plus some conditions. And in order to properly restrict this adjunction, there was some question mark here. What should be here? And the notion that is here is this notion of a reverse omega automaton, which intuitively is exactly something that needs to behave as the reverse of omega automaton. And maybe just a bit more that I can say is that these omega automata can be characterized by some specific conditions called circularity and coherence, which are well, basically a restriction or a condition on the languages they accept in a way. And here I have two similar conditions as well: algebra, reverse circularity and reverse coherence. But I'm saying this more for if you want to ask me later what these mean, because I don't really plan to explain them in detail. And then the second adjunction is between algebraic reverse omega automata and the reachable algebraic reverse omega automata. And this is actually very, very similar to an adjunction between DFAs and reachable DFAs. So this is actually to a large extent just notice that the same thing works for omega automata. As I told you, it often does. And the last part is the adjunction between reachable algebraic reverse omega automata, and this is the category of quotient Wilke algebras.
What does reachable mean?
Yes, I should have said it probably. Thanks for the question. It means that every state is reachable from the initial state by some transitions.
Right, that makes sense.
Yes, and this adjunction actually is, well, from reachable to arbitrary, I go by inclusion, and in the other direction, I go by taking only the reachable states and dropping all the rest. Yeah, thanks for your question. And for the third adjunction, actually, these will and ought, they're, well, we had to come up with two new transformations because, well, the transformation in one direction didn't exist, and in the other direction there was something, but for our purposes, I'm not sure if it really would work. And what these do, just maybe very briefly, is if we're given a quotient Wilke algebra, we can actually think of it as an automaton, but an automaton that reads things backwards. Because forwards, there's some problems with the reading of the words. And then for its adjoint, we actually want to see the automaton as, well, see all the paths of the automaton in some way as elements of an algebra, but because this was actually taking everything backwards, this also needs to do everything backwards, so paths backwards in a way. And this as well is something you can ask me later to give you in more detail. So for now, I just want to end with a summary, which is that we saw that omega regular languages can be characterized by Büchi automata, or by omega automata via the lassos, or by quotient Wilke algebras via the ultimately periodic words. And we saw that there's actually this dual adjunction between one side of the picture, omega automata, and the other side, the Wilke algebras. So thank you for your attention. And please, if you have questions. Yes.
Those adjunctions remind me a little bit of a paper by Clemens and Prakash and a million other people. But I don't know, maybe you should know. You were on it too. Okay.
That is true, it's a very long.
Yeah. So I don't know, what is the connection? To that
The reverse
paper?
determinized.
Other reverse
Essentially the
determinized.
same.
Yes. So, so in this adjunction, this reverse determinized is actually, this adjunction can be obtained as a lifted version of some other adjunction between the categories, well, set and set up, and this adjunction can be seen in the same way as a lifted version of an adjunction between set times set and the op of that. So it's actually not only is it the same reverse determinized, but it is the same way a lifted version of a base category adjunction. And then
Duality, right? It's stone duality, sort of. You sort of know.
I think it's really a bit simpler because it's just a contravariant power set functor.
Okay.
And then the only tricky part is because when we start talking about these omega automata, then there's some more. It's not only this lifted version. We have to be careful about which exactly objects we need to keep. Yeah, thank you. Ezra?
So maybe also connecting to this, does this also give you like a Brzezinski algorithm for minimization, or omega automata?
It does. It does. Yes, Mike did this in his thesis, and I just want to. Yeah, so there were previous minimization algorithms described by Chandra and Feynman, but I think Mike for the first time described the Brzezinski style, and it does work. Yes. Yes.
Do you get any less consequences for free as a consequence of having this long chain of adjunctions?
Yeah, so we looked at some like preservation of syntactic Wilke algebra goes to what automaton, and initial automaton goes to what algebra. I would say we don't have some very striking consequences of it yet. Hopefully in the future.